The exponential, or also sometimes called complex continuous time Fourier series, is just another form of the Fourier series, apart from the trigonometric form. It says that if we have a periodic signal, x of t, with fundamental frequency omega 0, then we can write x of t as an infinite sum for n going from minus infinity to plus infinity of dn times e to the jn omega 0 t. So x of t with fundamental frequency omega 0 can be expressed as an infinite sum of complex exponentials that have frequencies that are multiples of omega 0. So in order to find the exponential or complex Fourier series coefficients, what we're actually trying to find is those coefficients dn, which are given by the formula dn equal to 1 over t0, then the integral over one full length of the fundamental period t0, x of t e to the minus jn omega 0 t dt. And again, t0 is the fundamental period of the system, and it's given by 2 pi over omega 0. Of course, there is a connection between the coefficients of the complex or exponential Fourier series and the coefficients of the trigonometric Fourier series. For instance, dn, the coefficients of the exponential Fourier series, are given by a0 for n equals 0 by 1/2 of an minus j bn for n greater than 0, and by 1/2 a minus n plus j b minus n for n less than 0. Let's have a look at a very common example, the square wave, with fundamental period t0 and tau being the width of the square, which goes from minus tau half till plus tau half. In formulas, x of t is given by 1 between minus tau half and tau half, and 0 for tau half being less than the magnitude of t being less or equal to capital T0 divided by 2, with the fundamental frequency omega 0, which is equal to 2 pi divided by T0, and the fundamental period T0. To calculate the coefficients of the Fourier series, we'll use the formula for dn. It's equal to 1 divided by T0 times the integral over one full period T0, x of t e to the minus jn omega 0 t dt. The integral has length t0, and here we will choose to take the integral between minus t0 half and plus t0 half. During some times of this interval, the signal is 0, so it does not contribute to the integral. However, in other parts of the interval, the signal is equal to 1, which will contribute to the interval. Using this allows us to simplify the formula to 1 over t0 times the integral now from minus tau half to plus tau half of x of t, which in this interval is equal to 1 times e to the minus jn omega 0 t dt. Let's start by evaluating dn for n equals 0. Then d0 is given by 1 over t0 times the integral between minus tau half to plus tau half of 1 times e to the minus jn omega 0 t, where n is equal to 0 dt, such that we have 1 over t0 times the integral over minus tau half to plus tau half of 1 dt, which is 1 over t0 times the length of the integral, which is simply tau, so that dn is equal to tau divided by t0. For the other values of n, which are not 0, we'll go back to our simplified formula for dn, which is equal to 1 over t0 times the integral of minus tau half to plus tau half times e to the minus jn omega 0 t dt. Since this is a simple exponential function, we can solve the integral, which leads to 1 over t0 times minus e to the minus jn omega 0 t divided by jn omega 0 evaluated at minus tau half and plus tau half, which is equal to 1 over t0 times minus e to the minus jn omega 0 tau half over jn omega 0 plus e to the plus jn omega 0 tau half divided by jn omega 0, which we can also write as 1 over t0 of e to the jn omega 0 tau half minus e to the minus jn omega 0 tau half divided by jn omega 0. Using Euler's formula, sine of x is equal to e to the jx minus e to the minus jx divided by 2j, this can be rewritten. So dn is equal to 1 over t0 times sine of n omega 0 tau half divided by 1/2 n omega 0. Using the expression for omega 0, which is equal to 2 pi divided by t0, allows us to further simplify the formula for dn, which is equal to the sine of n pi tau divided by t0 divided by n pi. Defining that sine of pi x divided by pi x is equal to the sinc of x. This yields that d of n is equal to tau divided by t0 sinc of n tau divided by t0. Plotting the coefficients dn as a function of n shows the form of the sinc function. Here we have chosen tau being equal to pi half and t0 being equal to 2 pi. So in order to express the square wave as a function of complex exponentials, we need an infinite amount of complex exponentials, where the complex exponentials are weighted according to the coefficients dn, where the coefficients are relatively big for low values of n, but then decrease and approach 0 as n goes to infinity. Here you see an example of a slightly different square wave, where it doesn't alternate between 1 and 0, but instead between 1 and minus 1. This square wave can of course also be expressed as an infinite sum of complex exponentials. However, since the mean or the average value of the signal over time t is 0, the coefficient d0 will also be 0. Apart from that, the coefficients dn also form a sinc function as we derived above. When approximating the square wave only with a finite sum, this is only with a finite number of complex exponentials, we get an approximation of the square wave. For example, here we see approximation of only one cosine wave. This is taking the coefficients d1 and d minus 1, but ignoring all other coefficients. Adding more coefficients allows us to better approximate the square wave. But in order to make sure that we get the exact square wave, we have to use the infinite sum. So any finite approximation will always differ slightly from the perfect square wave.